All right, let's start. Okay, so last time we studied this exponential random variable, and one interesting property of this exponential random variable was something called a memoryless property. And the memoryless property is something like this. And so the probability of a battery or our hard drive lasts for more than additional 5 years. Additional 5 years, given it already lasted for 3 years, and so the situation is it already lasted 3 years in the past so far, and then the probability of lasting for 5 additional years will be exactly the same as the probability of just a brand new hard drive lasting for 5 years, right? So that is this memoryless property. So if our hard drive its lifespan follows this exponential distribution, and then even if it's just a 10-year-old hard drive, it will work as just as new as the brand new one. Okay. So that was this memoryless property, and then we briefly studied how we can derive this property in the case of memoryless, this exponential distribution. Then at the end of last class, we studied about this when we have a maybe n different hard drive that if we have a 10 different hard drive each of which follows its own exponential random variable or exponential distribution with its own parameter lambda 1 through lambda n, and then the mean of these random variable, which is a function of our random variable, it is also exponential random variable, and then the parameter will be the sum of all these. And so so that is one interesting property that we had. Let's see. Okay, and then now today let's study the new distribution. So the first one is called this chi-square distribution. Okay, so let's study what this is, and then we first think about some repetitive sampling of standard Gaussian distribution. So suppose we have Z1 that follows the normal distribution or Gaussian distribution of zero mean and standard deviation of 1, and then suppose we have another Gaussian standard Gaussian distribution of Z2, which follows its own zero mean and unit norm, unit variance or the standard deviation. And so Z1 and Z2 are independent random variable. And then if we imagine a multiple of these independent standard normal or random variable, and then we consider their squared value, and then their summation of n independent standard normal random variable. So that is called a chi-square random variable. Okay. So again, we prepare for n independent standard normal random variable, and then we square of each value, and then sum them up, and then such a sum is called a chi-square distribution. Okay, and then let's first think about its mean value. Its mean value, and the mean of this random variable will be just the sum of each of our random variables zi squared, right? And then what is the expectation of zi squared? So zi will follow this standard Gaussian random variable, right? And we consider zi squared, right? And zi will have a zero mean, and so it can be viewed as zi minus 0, which is its own mean value, and then squared value, and then take the expectation. And that is called a variance, right? And then we know its variance is just 1, right? And so this part will be 1. And so we have n independent random variable. And so the expectation of this x, or the expectation of this entire summation, will be n, right? And then the variance, how do we compute the variance? It's a little bit tricky. And so, such a variance can be computed as this. So, suppose we have these two random variables. Okay, in this case, the variance of y will be variance of x1 plus variance of an x2 plus covariance of x1 and x2. And was there a 2 here, right? So if x1 and x2 are independent, and then this part will become 0, right? And then, we have the summation of these variance of these two. So how do we represent this guy? So here we have z1 squared and z2 squared. And then, let's think about z1 squared and this guy's, the variance of this guy, where z1 follows this standard normal random variable. And then in this case, let's think about its variance representation. Then it will be the expectation of z1 squared and squared, or this guy minus its mean value, and then squared value, right? And then what will be this question mark? What will be number in this question mark? Is it 0? Is it 0? So again, the mean value of z1 squared, what is that value? The mean value of z1 squared. So this question is certainly different from this guy. What is this guy? This guy is 0. And what about this guy? It is what? How much? What is the value? It's 1, right? That is what we just computed here, right? It will be the variance of this standard normal Gaussian distribution. Okay, so we have to have 1 here. Okay, and then if we expand this representation, and then it will be like, something like this, right? And then we know the expectation of this and this. But what about this? Do we know the expectation of this? So, do we know, the expectation value of z1 to the power of 4? In this case, we cannot easily answer that, right? So in that case, we have to compute something called a moment generating function that is out of scope in this class. So you don't need to worry about this, okay? And then also, we also skipped one distribution called a gamma distribution. And this gamma distribution, the special case of this gamma distribution is this chi-square distribution. So we can think about the normal distribution, and then when setting the mean and the variance as 0 and 1, respectively, in that case, we call it as a standard Gaussian distribution. So we have a Gaussian and then standard Gaussian distribution, which is a special case of Gaussian distribution. So we can think of this relationship between the gamma distribution and this chi-square distribution just like that. So we have a kind of larger category of a probability distribution called a gamma distribution. And then when setting up a particular parameter value in this gamma distribution as some particular value, and then that is corresponding to this special case of this chi-square distribution. And then we can derive the mean and the variance in the case of a more general case of a gamma distribution, and thus utilizing that, we can also derive or compute the mean and the variance of this chi-square distribution. And then I'm going to just to tell you the variance will be 2 times n. Okay, and then yeah, let's just try to remember what we learned. So suppose the variance, the mean value is n, and the variance is also the same as the mean value. What was the distribution that has this same mean and the variance value? What was the example of a distribution that has the same value of mean and the variance? What was that? Does anyone know? Okay, I'm going to give you a bonus point. Poisson distribution, right? Yeah. So yeah, this class, yeah, you need a little bit of a memorization on these stuff, which I don't like about this class. But yeah, in the case of other, unlike other math courses, it requires a little bit of a memorization of these, characteristics of several different distributions. But anyway, Poisson distribution. So yeah, let me ask another question: is Poisson distribution discrete or continuous? It's a discrete random variable, right? Poisson distribution is discrete, and then its mean and the variance was actually the same, right? But it has its own probability distribution kind of mathematical expression, right? But in this case, even though, it's a completely different distribution, but interestingly, it has like this kind of proportional relationship between this mean and the variance. So if mean value gets larger and larger, and then the variance will also get larger and larger. And what was the mean value? What was the mean value of this n? This is simply the count of our standard random variable, standard normal random variable, right? So if we sum up the 10 squared value of standard normal random variable, and then such a chi-square distribution will have the mean of 10, right? Because each of our zi squared will have the mean of exactly 1, right? And so this n is called a degree of freedom, because we have n different freely chosen random variables. Okay. So if we have more number of random variables that can have many different values, then the variance will correspondingly become larger and larger. Okay, and so this is the distribution of this chi-square distribution. Depending on the degree of freedom, it will have a different shape. Okay, and so yeah, this chi-square distribution will have a single parameter value, which I just mentioned as this degree of freedom. And then, so I mentioned about this representation, right? So yeah. So this representation in the case of alpha becomes 0.1 in this case, for example. And then, yeah, n is fixed. Suppose n is, for example, 10. And then suppose this is a probability distribution or probability density function because it's a continuous random variable. And so suppose this one is the case of n being 10, or degree of freedom is 10, and then if alpha is 0.1, and then the area on this part should be 0.1, and then this threshold value is called this chi-square distribution, and when alpha is 0.1 and when n is 10. Okay? Suppose this value was maybe 13, and this guy is 13, which is our threshold value. Okay? So that means when summing up the squared Gaussian random variable, 10 different squared Gaussian unique standard random variable. Yeah. And then, the probability of such a sum of squared standard random Gaussian variable become is equal to or larger than 13. That probability will be 10%. Okay? That is the meaning. And this value, okay, this value is 13. Okay, and then, so I probably should have mentioned about this representation. So if we, so just like this, or in this case, we call this random variable as, usually as z, right? So if a certain random variable follows chi-square distribution, we especially give a notation for this chi-square distribution as this, because this is called a chi and then chi-squared, and when this chi-squared distribution has a degree of freedom as which is n. Okay. Yeah, and this chi-square distribution is quite useful in some of the later chapters. So please keep this in mind. So it will be useful at some point in many problem solving and hypothesis testing and so on. Okay, and then the next one is this T distribution. T distribution. Yeah, so this one involves chi-square distribution, and it can be viewed as like a composite function. So so let's think about this composite function. So x is transformed as a sine x, and then this guy, so f of an x is sine x, and then so y is a sine x, and then z is y squared, and in this case it will be sine squared x. Right? It's just one example of this composite function. What is it called in Korean? In this case of multiple steps of functions, what is it called in Korean? What would it be? Sums. So that is sums is called a composite function. The deep learning and this kind of neural net is actually one special example of this composite function. Okay, and so so here you can view it as a kind of composite function. So we first obtain standard normal random variable z. Okay, so we do kind of composite multiple steps of obtaining this kind of function. So we first, at the first step, we first obtain a sample of this standard Gaussian random variable. Let's call that as z, and then we do another separate step of obtaining one random variable value, and that is this chi-square distribution that just we studied in the previous slide. Okay, so we have two separate processes, right? So one is obtaining this, and then the other is obtaining chi-square distribution. And of course, we have to specify n. Okay, n is a predefined parameter that we have to determine in advance. And so suppose n n is 10, and then we obtain 10 different standard normal random variable value, and then take the square of them and then sum them up, and then we obtain one sample of chi-squared distribution when degree of freedom is 10. That is called this xn squared, right? And certainly this guy and this guy is a two different one. Okay? And then we divide it by this, and then we obtain this representation as the second step of function by utilizing those two intermediate output of z and xn squared. Okay. And then after all, this is called a T distribution. Okay, student T distribution. Okay. So let me see if it has the but anyways, it's called a T distribution, but also its full name is a student T distribution. I don't know about the details about the story about why it is called that way, but some graduate student may have found this interesting distribution, and that way instead of giving his or her own name, he's just the student, so that's why he gave this kind of name. But that's just my own hypothetical story. But anyways, this is a T distribution, and then what was the parameter that we had to give in advance? The only parameter was n, which was used to obtain this chi-square distribution. So correspondingly, this T distribution will have the parameter n, which comes from the chi-square distribution. Okay, so in this case, we call it as T of an n, and it's called the T distribution with n degrees of freedom. Okay. Okay, then let's focus on this part, the denominator part. So the denominator, the numerator is this standard Gaussian random variable, but in the case of denominator, it is this guy, right? And then let's think about this, and then it is this, the sum of squared value of this standard random standard Gaussian random variable, and then what was the mean value of this chi-square distribution? So each of them had the mean value of 1, and then this mean value was n, right? And then this guy has the mean value of an n, and then divided by n, right? And then the mean value or expectation of this part or this denominator part will also be 1, right? Also be 1. And so if your chi-squared random variable was sampled around its own mean value of an n, okay, and then the denominator will be close to 1, and then it will have no effect. It will have no effect. In that case, Tn will be just like z, okay, just like a standard Gaussian random variable. But in practice, xn squared will be away from its mean value of an n. It could be less than n, or it could be larger than n. In that case, it will have an effect of sometimes increasing or decreasing this standard random variable z, standard normal random variable z. Okay, so if we remove this denominator part, it will be just z, and then what was the distribution of z? And then it is something like this, right? But this z sometimes will become larger and smaller, and thus it will have a little bit more fluctuation depending on this chi-squared xn squared value. Okay, so that way, the distribution will be something like this. Let's see. Oops. I have I didn't include the figure which was originally in the book. So suppose this is our Gaussian distribution. I mean unit Gaussian distribution. And usually your t distribution will be something like this. Okay. So what I want to emphasize here is that so this is t, and this is just the normal distribution with the standard univariates. So this t distribution will have a thicker tail, because even if this c value was obtained as maybe 2, okay, and then what is the probability in this part? What is the probability? So approximately it's 1.96, and so yeah, minus 1.96 and plus 1.96. How much probability do you have inside of it? How much? What was the confidence interval and the corresponding probability? Or what is the probability of minus 1.6 and plus 1.96? And in the case of z, following this standard normal, then what is the probability? It is 95%, right? And so what is this probability? It is this part will be 47.5%, and so this part is 2.5%, right? And then what is this value? Or what is this 1.96 value? So by following the convention that we used in our notation, it is z of what? 0.025, right? So that was our notation. And what was that? This value. So we need to have the value in this part as this probability value. And the corresponding threshold value will be represented as this notation, right? But anyways, yeah, back to this t distribution. I mentioned that t distribution will have more fluctuating effect. So sometimes it will become larger or smaller due to this part. So in terms of its variance, these are a little bit extreme value, like 2 or 3 or 4. Probability of observing these extreme or these relatively large value will be really small in the case of unit normal Gaussian distribution, the standard normal Gaussian distribution. Right? But due to those fluctuating effects, even if it's a larger value, its corresponding probability will be a little bit higher than the standard normal random variable. Okay? So that way, the student t distribution will have a thicker tail, or as we go to this extreme value, the probability will be a little bit larger than the unit standard normal Gaussian random variable. Okay. Okay, so by utilizing this fact, by utilizing this property, so let me show one example. Have you heard about this TSNE, something called the TSNE? Yeah, personally, I utilize this method a lot in my own research. It's one of the 2D embedding method or visualization method of high-dimensional data. So let's see. Let me see if I can find some interesting example. Okay. So does anyone know the website called the Reddit.com? Reddit.com. Reddit.com. No one knows? Reddit. R-E-D-D-I-T. It's a quite famous website in the US. And so, yeah, if you're interested in, for example, like machine learning or deep learning, So where do you get the most up-to-date or the most state-of-the-art or recent information? That's where you can obtain such kind of information. So that is a kind of community website, just like a Twitter or like Facebook. It's just a social media website that the people in the US uses a lot. But that's just a text-based. It's not as fancy as Facebook or not heavy as Facebook or something like that. That's that. But in this Reddit, there are many different subgroups depending on its topics. Okay, so there is one subgroup called a machine learning. Okay, within that subgroup, which is called a subreddit. Okay, subreddit. Yeah, subreddit. It's just a particular group of just like a neighbor cafe or something like that. Okay, depending on a particular topic. And then if we collect all the documents posted within that particular neighbor cafe, for example, and then we construct a hybrid and a feature vector for each of these cafes. And then we can visualize them in this 2D scatter plot. And then, if you see them, each dot is representing one neighbor cafe. So somewhere here, one dot is corresponding to machine learning cafe, okay, or machine learning subreddit. Okay, and then if we visualize them, and then we can get some kind of high-level overview about our data. So, for example, there are some interactive version of it. So if you click it, and then you can see more detailed information. It's just a Python library for this interactive visualization capability called a bokeh. But anyways, So, I'm not sure if it's appropriate, but do you guys know what the LGBT means? LGBT. Yeah. So, it's lesbian, gay, and bisexual transgender. So those are minority in terms of these sexual preferences. So there are multiple neighbor cafes for them. Okay, and then if you see around here, you see some sexual related kind of cafe as well. Okay, and then also I don't know why, but those music related ones are closely related. According to this kind of visualization. Okay? So I don't know why, but somehow they have some overlapping topics or some contents that are overlapping between these two different topics of cafes. Okay, and then on the very opposite side, we see these soccer. So you can understand them. You can understand that this soccer is quite unrelated to those sexual related things. Okay? Maybe those that are interested in soccer may not be interested in those sexual related things. But at the same time, those NFL is also a national football league in the US, and they are also closely placed. So that way, you can kind of get some kind of overview of what our data. And the main technique used here, to generate this kind of 2D scatter plot, that is called a TSNE, or T-distributed stochastic neighbor embedding, and that utilizes this student's T-distribution. Okay. But here back to the slide, the point that I wanted to make is the T-distribution will have heavy tail property compared to this standard normal random variable. Okay, and then let's think about the value of an n. When n is small or large, in those cases, which one will get more fluctuation? Which one will get more fluctuation? So if we think of n being really, really, really large, if n is really, really large, and then it will, although, maybe x chi squared where the degree of freedom is maybe 10,000. In this case, we will just have an, so this one divided by n will be just the average value of zi squared, right? So it will have the mean value of 1, of course, I mean, when it was divided by n, right? So its mean value or expectation will be 1, but its variance will be a lot kind of smaller, right? Because we are averaging many different values. Then, let me ask the question. What is the variance of this guy? Given the fact that the variance of an x or chi-square distribution is 2n. Okay? So x, again, is this chi-square distribution of maybe 10,000? Yeah, chi-square distribution. And then this one, the variance, variance of this will be 2 times 10,000, right? And then what about chi-square distribution? Yeah, chi-square variable divided by n. What is the variance of it? It will be the original variance divided by n squared, right? Right? What is n? N is 10,000, right? And so the variance will be smaller and smaller. So the distribution will have a stronger and stronger peak around its mean value, and the mean value of it is just 1. Right? So it will have less and less effect. I mean, in terms of a fluctuation, when n gets really large. So if n is really large, and then it will be just be in this case of this t distribution, n becomes really large, and then this t of an n will be just converging to the standard normal random value, right? And then if n is a really small value, maybe 2 or 5 or 10, then it will have a lot of fluctuation. And then it will have an effect of having a large tail, okay, thicker tail. So that way, if n is 1, and then it will have more thicker tails, and then n gets larger, and then it will have a less thick tail, and then n gets large, and then it will have more peak around 0. But let me ask the question. So if n gets really large, like 10,000, and then will it be like this? Will it be like this? What do you think? What's the convergence, or what's the converging shape of this distribution? It will be standard normal, right? Standard normal. It cannot be like a sharper. I mean, it cannot be sharper than the standard normal, right? So it has a certain width. We call our z in the numerator here. Okay, so this one has its own variance, right? So it cannot be really like infinitely sharp, right? So the sharpest shape will be our standard normal random variable. Okay, then the mean value of this student t distribution will be 0, and then the variance will be this form. Okay? So we cannot prove, or we cannot understand the proof of these. And yeah, of course, this one we can easily derive that. Right? And so we can just do the expectation of it. And then we can easily obtain the expectation of it being 0. But in the case of variance, we cannot easily prove it. But I just want to note that this t distribution is also another special case of gamma distribution that we didn't run. Okay? The chi-square distribution and t distribution are both like its own special form of gamma distribution, and thus, if we can derive the gamma distribution's mean and the variance, and then it's just easy to obtain this mean and the variance in these special cases of distributions. And then, from this this thing. So yeah, the variance is slightly larger than 1, right, from this point, right? So that's the same thing as the effect of a fluctuation. So if it was just a pure standard normal random variable, then you will have exact value of 1 as variance. So you will have a variance of exactly 1, right? But you will have slightly larger variance than 1. But if n gets larger and larger, then it will converge to 1. Okay? Then I believe you guys can understand now this, right? So alpha was 0.1, for example, and then we have this t distribution, and then the corresponding area is 0.1, and then suppose n degree of freedom was maybe 10, and then alpha being 0.1, and then it will have some value around here, right? Okay, so that is the definition of this t of alpha comma n. And then there are, so if you look at the back of your book, and then there are some tables of this t of alpha comma n. So for various combinations of n and alpha, and then you should be able to find some table in the back of your book. Okay, but in your book, alpha is ranging from 0 to 0.5. Okay. And then what if we want alpha being maybe 7, which is larger than 0.5? In that case, we have to utilize the table here. So yeah, it's really simple, but yeah, points. Yeah, so alpha was 0.7, and then this guy is 0.7, right? And then yeah, it's a symmetric one. So the distribution is symmetric. So this part is 0.3. And then we think of here, right? And then this one is t of alpha being what? Alpha being 0.3, right? For maybe n being 10. Okay, so n is fixed. Okay, and then this value, yeah, is symmetric. So this value is just a minus this value. Okay, so that way we can utilize this symmetry. Okay, so yeah, so that is corresponding to this. And then we can easily derive this part. Any questions so far about this t distribution and the chi-square distribution? Okay, then the next one is yeah, what we call F distribution. So this one will be also used in the later chapter. So please keep this in mind. So in this case, F distribution can be viewed as some kind of distribution of this ratio. Okay, ratio, and ratio between what? So we consider two different chi-square distributions. Okay, so we have a chi-square distribution of degree of n and m. Okay, so suppose n was 10 and m was maybe 25. Okay, and then we do the separate kind of sampling on 10 different Gaussian random standard Gaussian random variable and 25 different standard Gaussian random variable, and then take the square of them and then sum them up on 10 of them and 25 of them. And then we form these two separate chi-square distributions. And then we divide it by its degree of freedom. Okay? And then we consider its ratio. And that function of these random variables is called F distribution, or this random variable of this F distribution. Okay? Okay, and then let me ask the question. So for each of these denominator and the numerator that forms this F distribution, can each of them or any one of them be negative value? So yeah, it cannot be negative value. Or yeah, more fundamentally, chi-square distribution will be only defined for positive or non-negative value of random variable. So it cannot be negative value, right? So if we recall, yep. So if this shape of distribution is only defined on the positive side of an x, right? Because yeah, the squared sum will always be greater than or equal to 0, right? Okay, and then here, this one will be positive and this one will also be positive. And then, yeah, we consider the ratio of these two positive numbers. And yeah, if this value, yeah, each of these values, let's think about the mean value. So their mean will be 1, right? So their mean value will be 1. I mean, each of them, okay? And so the ratio will be approximately have a mean value of 1. But if we have really large value on this part and small value on this part, and then this f value can be really large, right? This ratio can be maybe 100 or 10,000 or maybe hundreds of thousands, right? And then it can also be really small, but it can be close to 0, but it can never be negative value because we are considering the ratio between the two positive numbers, right? And then if we think of this a parameter, and then we have two parameters, n and m, which are the two degrees of freedoms of the chi-square distribution used in the numerator and the denominator. Okay, so it has these two parameter values. And then we can also think of this value, so f of alpha being 0.1, and n being 10, and m being 25, and then you know what that means, what this value means. So this is simply the threshold value that contains the probability to the right as 0.1. Okay, there is one interesting property. Let me see. So yeah, I'm gonna skip the proof, but you can follow yeah, this kind of equation. Okay, so it's just like the same as what we did in this part. So if we wanted to obtain the threshold value that contains more than half of a probability, or 50% of the probability, and then we have to utilize the other side of value. And so in this case, a little bit, the relationship is a little bit tricky, but you can easily compute this, right? Yeah, or prove this value as well. And then, yeah, so this F distribution, I don't know if our book has the distribution, but let me just search for it. Okay, so this is the usual shape of F distribution. It's quite weird, right? But approximately, we can view the peak or the mode at around 1, right? Because each of the numerator and the denominator will have the mean value of 1, right? Yeah, and so approximately the mean value will be 1, and then yeah, the distribution is certainly not symmetric. Right? So it is only defined on the positive side. Then yeah, that's how weird shape. Okay. Yeah, sometimes it doesn't even have a kind of peak value around 1 in the case of n being 2 and m being 4. Yeah, so that is the shape of this F distribution. Oh, there are many different examples here, but yeah, you can search for images in the Google image search. And there was this F distribution. So at this point we didn't know, or we didn't study where to use this T distribution or F distribution and so on. But these distributions are utilized in something called hypothesis testing. And that hypothesis testing is quite a useful technique that you can have. So we will study in maybe in a month or so, or even less than that. Earlier than that. Okay, so any questions so far? So that's the end of chapter 5, I think. Okay, then let's check the attendance. 우리요? Okay, let's discuss about it first. So the exam period starts from October 20th, which is a Friday, and then until the following Thursday, which is October 26th, right? So we have two options. So we will have an exam during our test time. And then which one do you guys prefer between 24? Which is Tuesday, and 26th on Thursday. 24th. 26th. Okay. So the exam will be on 26th. Any other questions? 시험 보니까 나를 행복해지나 봐요. 여기저기서 봐. 범위요? 적당히 뭐 어디까지 배우면 데까지. So the exam scope will be, I think certainly we will cover the entire chapters, in chapter 6 entirely, which is an expectation. The sample mean and the sample variance. So we already studied the expectation. And then before then, we will have maybe one more homework that will be distributed, and then we will be collected before our exam. Okay. So please think of it as a training process of yourself for the exam. Any other questions? 오케이. 출석 부를게요. 오늘은 출석부를 제대로 된 걸로 뽑아서. 송하은, 김봉한, 하여튼 이제부터 늦게 오는 거 이제 인정 안 해줘요. 뭐 지금 더 늦게 올 수도 없겠지만. 그리고 신광록 없죠? 백승택, 곽성원, 두반 콜니, 손낙원, 함태경, 이민석, 김도훈, 이희인, 라파엘, 알마디, 레이안, 이지웅, 제한재, 김형진, 이은비, 하미도프, 압둘라지즈, 사동회, 최병록, 류도, 진스, 나종환, 임특, 김홍우, 제슬린, 제니퍼, 왕운용, 조야오수에, 정재현, 김연학, 나탈리시오, 임규정, 요천우, 알가넴 술탄 칼리드, 아칸시 디브컬, 임준혁, 지아이팬, 임혜수, 윤창규, 장덕연, 배진호, 이수영, 최지훈, 김민수, 임현진, 차윤학, 정영훈, 강필고, 허경무, 윤현주, 남기웅, 장효엘, 정기동, 조재우, 안수영, 효리, 소명현, 김승우, 유영우, 정명재, 문형돈, 최옥호, 이재후, 최원미, 과묘, 유미연, 임준상, 이세정, 왔는데 어디 갔죠? 고한건, 김민창, 없죠? 김동희, 네.